My name is Gabby Lamb, and today I will be talking about the valence bond theory for sulfur hexaiodide, and I will be talking about the Lewis dot structure, the VSEPR, the box diagram, and contour diagram for this molecule. I'm first going to discuss the Lewis dot structure, and this is going to help us determine the VSEPR for this molecule. So with the Lewis dot structure, we're going to first determine the amount of valence electrons that are within the molecule to help us draw the structure. Now, sulfur has 6 valence electrons, and iodide has 7 valence electrons. But with iodide, there are 6 within this molecule, so what we have to do is times the number of valence electrons of iodide with the number of iodide atoms within this molecule. And when we times those together, we get 42. Now, to determine the total amount of valence electrons within this molecule, we add together the 6 electrons from sulfur and the 42 total valence electrons from the 6 iodide, and then we get 48 total valence electrons for this molecule. Now, with drawing the Lewis dot structure, we're going to put sulfur in the middle, and then we're going to have all 6 iodides surrounding it. There are no lone pairs within this molecule, so we don't have to worry about that. Now, sulfur is able to have 6 bonds surrounding it because it has a d orbital available to it, and it does not follow the octet rule. We wouldn't be able to do this with oxygen per se, which is in the same period, because oxygen does follow the octet rule, and it does not have a d orbital available to it. Now that we have the Lewis dot structure drawn, we can now determine the electron geometry of this molecule, which in turn helps us determine the molecular geometry of this molecule, and then which in turn to that will help us determine the VSEPR of this molecule. So we look at the Lewis dot structure, and we see that there are no lone pairs, but there are 6 iodides surrounding the sulfur. The 6 iodide will represent 6 electron clouds, and with 6 electron clouds, we can then determine the electron geometry, which will be a octahedral. Now that we have determined the electron geometry, we can now go into determining the molecular geometry, and then drawing the VSEPR. So in the last slide, we determined that the electron geometry was octahedral, and the molecular geometry would differ from the electron geometry if there was a lone pair present, which there is not. So this means that the electron geometry and the molecular geometry are the same, and that is the octahedral. So to start off drawing the VSEPR for an octahedral, we want to start off by drawing a rectangle, and this will represent our plane. And we want this to be a 3D structure, or represent a 3D structure at least. So we're going to draw 2 lines at the top and bottom, and these will represent the iodides that are at the top and the bottom of this VSEPR. And then we're going to draw 2 solid lined triangles, and these solid line triangles will represent the 2 iodides that are protruding towards the front, and then these dashed triangles are going to represent the iodides that are protruding towards the back. So since we have no lone pairs, we do not have to worry about lone pair to lone pair repulsion or lone pair to bonding pair repulsion. And bonding pair to bonding pair repulsion is almost negligible. So we're going to have here all angles being 90 degrees. So on this slide, what I have shown are some different 3D models, as well as different views on these 3D models. So on the left, I have an electronic 3D model of the molecule, and then on the right, I have a 3D model that is made by a model kit. So we look on the left side of this slide, and we have the two molecules. On the top, we have a more side view of the molecule, and on the bottom left, we have an aerial view of the molecule. So we're going to label these real quick. This middle atom is the sulfur, and surrounding it are the iodides, as well as on the bottom here, these are showing just the iodides, the purple. And then on the top left, this is going to show better the 90-degree angles that I stated on the last slide. So we see here, this makes a perfect 90-degree angle, and then these can be found throughout the model. And then we look at the bottom left, and the rectangle that I'm drawing in is representing our plane. And then we can also see some perfect right angles here, which then we can conclude that all angles are 90 degrees. So when looking on the right-hand side to those two pictures, I'm going to first discuss the bottom right picture. This is just the same as the bottom left picture. It's just shown with the model kit instead of an electronic version. Now with the top right, I'm going to draw in the iodides and the sulfur to give a better picture. So I am first going to draw the solid line triangles pointing towards the sulfur, and I said those represented the iodides that are protruding towards the front. And I am then going to draw the dashed triangles that are pointing away from the sulfur, which I said represent the iodides protruding towards the back. And then the two lines I am drawing are pointing towards those iodides at the top and the bottom, which I said represented the top and the bottom of the molecule. Next, I'm going to be discussing the box diagram for sulfur hexaiodide. And what the box diagram explains that the VSEPR doesn't explain is how the iodides fit in with the sulfur. So we're going to look over to the left side of the screen. And what that is representing is the ground state of sulfur. Now only 3s, 3p, and 3d are being shown because the 1s, 2s, and 2p orbitals will just take up space, and we're really only focusing on the 3s, 3p, and 3d orbitals. So we look at the ground state, and we see that there is only what we call 2 parking spots available for the 6 iodide. Only having 2 parking spots only allow us to have 2 iodides with the sulfur. So what we need to do is take these 2 electrons being circled, and we need to promote them to the d orbital. Energy was added so that we were able to promote those 2 electrons, And now we have 6 parking spots, which is highlighted by the red circle. And this gives us the excited state of sulfur, which is represented by this star right here. So we take those 6 parking spots, and now we hybridize them. And this gives us the sp3d2 orbital. And it is this orbital because we have the 3s, all of the 3p, and 2 of the 3d being utilized in the hybridization. Now we have the 6 parking spots available, and we have here the 6 iodides, and I have the iodides times 6 here because it would be too messy to write out all the iodides. So iodide is in the 5p orbital. We have 1 electron here that is unpaired from each of the 6 iodides. And that electron, or those 6 electrons, are going to go to each parking spot. So we're just going to draw lines there. Showing that. And then we can fill in those parking spots, giving us what was shown in the Vesper, an octahedral. And it is also shown in this picture right here. We have the iodide being shown in purple and the sulfur being shown in yellow. Next, I am going to be drawing the contour diagram for the molecule. So first, what I did is that I drew the plane of the molecule and some lines going across, and this will give us a guidance of where everything should go. So sulfur is shown here in the middle. I'm going to rewrite that in red so it's better visible. And then we have the iodides all around the outside. Now, these circles in red are representing the sulfur atom, and sulfur is smaller than iodide, so sulfur is shown here as smaller than the iodide, right? That is shown here. This is the iodide in green. So those red are shown all throughout because there are 6 spots available with sulfur. And then the brown dots at the top are the electrons that are being shared between sulfur and iodide. And then we have the green infinity sign representing iodide. Now, with these red circles representing sulfur, they are all, each one is an sp3d2. And it's not written in because it would just become a mess and really ugly. And then we have the iodide coming around the electrons that are shared with sulfur and coming back around. And the iodide is a 5p, and that is written within each iodide. Now, since it is a single bonded, there's no double bonds present. All these bonds are sigma bonds. And there are no lone pairs. So all of these bondings are bonded pairs. And then these are also going to be all right angles. or equal to 90 degrees. Here are just two more electronic 3D models. This is just showing the contour diagram, the atomic orbitals, and then this 3D model right here are showing the atomic orbitals, but they are showing the overlap between the sulfur and the iodide right here. And this is where, right here would be where the electrons are being shared.